Okay, in this video now we're going to go over an example. So I'm going to go over the example in the book of 10.4, where now that we have worked out in previous lectures the electric and magnetic field for a moving charge using the Leonard-Weichert potentials, then now we're going to apply it to a problem. So what this problem wants us to calculate is basically determine the electric field and the magnetic field for a charge moving with a constant velocity. Okay, so if it's a constant velocity, then there's no acceleration. The acceleration is equal to 0. Okay, so if that is the case, then what we can do is we can write out, we already have the formula for the electric field. So if A is 0, the electric field is going to be Q over 4 pi epsilon naught C squared minus V squared times R over R dot U, not V, but the velocity U, and then all of this times the velocity U. So just remember that the charge is moving with V, so V is the charge's velocity, and U is the speed of light in the direction of R minus that velocity. Okay, so okay, so can we do anything further with this? Well, I mean that's pretty much the answer for the electric field. But what we can find is that if we now look at the distance W, okay, so that W is, in previous chapters we always call that R prime, but so W is the distance from the origin to the charge. So here's our charge Q, here's the distance W, here's the point where we're measuring the electric field, and here's the difference script R. Okay, so W is just the velocity of the charge times the time. And so let's take a look. We can take R times the velocity U, and that'll give us CR minus R times V, which I can now rewrite as CR minus V times the time in the past minus TR times the velocity V. Okay, so with that, I can now cancel some things out. So basically these times here in the past cancel each other, and what I'm left with is C times R minus the velocity measured now, measured at the current time t. Okay, so that's R times U. So that would be in the numerator right here. Now if I look at the denominator says R dot U, and that's going to give me RC minus R dot V. Okay, which I can then rewrite as C squared T minus R dot V quantity squared plus C squared minus V squared R squared minus C squared T squared, and then all of that to the power 1/2. So essentially I'm just unwrapping this substitution that we made for the velocity u. So, okay, so now you can, if you looked at problem 1016, they solve this as r times c 1 minus v squared sine theta squared over c squared. So they're basically taking into account this, they write it in terms of basically polar coordinates, where r is now r minus vt, and theta is the angle between the position and the velocity. So there's a new coordinate system where you can now write it in terms of these quantities right here. So when you do that, I now write the electric field as Q over 4 pi epsilon naught c squared minus v squared c times r over rc 1 minus v squared sine theta squared over c squared square root of that, and then all of that cubed. Okay, so all we've done is rewrite the electric field in terms of different coordinates, and now I can rewrite this a little bit more as Q over 4 pi epsilon naught c squared minus v squared c times r, so the numerator doesn't change at all, and I can then factor out and get r cubed c cubed 1 minus v squared sine squared theta over c squared to the 3/2 power. Okay, so I just separated some stuff that was before, under that was being cubed. Okay, so now what I'm going to do is I'm going to basically multiply the top and the bottom by 1 over c squared, and when I do that, I get Q over 4 pi epsilon naught 1 minus v squared over c squared in the r hat direction divided by 1 minus v squared over c squared sine squared theta 3/2 r squared. Or another way of saying it is I took that c cubed in the denominator, canceled that c, made that c squared, and then divided the top and the bottom by c squared, which then gives me this. I also, what I did was, what I did was show that r over r cubed is the same thing as r over r, 1 over r squared, which then writes that as r hat over r squared. Okay, so that was the two things I did to get it into this form, but this right here now is a much cleaner looking form, which looks a lot more like a Coulomb's law. It goes as 1 over r squared, and a little bit easier to work with, because if I take the case of theta is equal to 0 or theta is equal to 180, then the electric field is q over 4 pi epsilon naught, 1 minus v squared over c squared, r hat over r squared. So again, it looks like pretty much a Coulomb's law, but now I've got this 1 minus v squared over c squared term. So if v is much, much less than c, then we really get Coulomb's law. Okay, now if we take the case where theta is equal to 90 degrees, now that sine squared of 90 is 1, and what we get is E is q over 4 pi epsilon naught, 1 minus v squared over c squared over 1 minus v squared over c squared to the 3/2 power, like so, which gives me q over 4 pi epsilon naught, 1 over the square root of 1 minus v squared over c squared. Okay, and now E is larger because I now have this extra factor of 1 over the square root of 1 minus v squared over c squared. So in the end, what you get is electric fields which are now kind of compressed in the middle and empty. So they're kind of compressed in the direction of motion of the charge, right here. Which is kind of an interesting result, where essentially now this electric field, which if it was just resting there, the electric field lines are going out radially, but now that the charge is moving along, those electric field lines get squished into the direction perpendicular to the direction of motion. Okay. If I now look at the magnetic field, so in the magnetic field, R, so I start with, say, this equation, and that gives me this, where I essentially have to get that r hat. If you look at this, this is now just r over little r plus v over c. So in the end, my magnetic field is 1 over c, r hat crossed E, which is 1 over c, r over r plus v over c crossed into the electric field. Now r crossed E is 0 because E is proportional to r. Basically, E is acting in the r direction. So r cross E is just going to give me a 0 because E is in the direction of r. So that means what I get is a magnetic field, which is 1 over c squared, the velocity of the particle, of the charge, crossed into the electric field. Okay. So what you see is that v much, much less than c, then 1 minus v squared over c squared is approximately 1, which means that I get Coulomb's law for the electric field, and I get this equation, which is essentially what you would get for a current. So therefore, at low speeds, we get basically the electrostatic cases.